In this video, we're going to do an explicit computation of computing the line integral of a vector field along some particular curve. In fact, we're going to interpret this in the context of the work done by a vector field on some particle that moves in a particular curve. Now, so what's our example? I have some vector field f of xy is yi hat plus nothing in the j hat component. And then I have some curve. It's the standard unit circle rotated around once counterclockwise. So let me first sketch what this looks like just to get a little bit of an intuitive feel for what's going on. So if I have just my normal xy coordinates, what does this vector field look like? So first of all, there's 0 j hat component. So all the vectors are pointing horizontally. Now also notice, it doesn't matter what the value of the x is, x never appears anywhere. All that matters is the height. So for example, if you are at height 1, so any point, any value of x, and then y equal to 1, say this point right here at 0, 1, the vector points exactly 1 to the right, 1 to the right, 1 to the right, and so forth. If the y value was twice that, say 2, then the vector would also be of length 2, and so forth. So this is a vector field that gets longer as it goes up. Likewise, if the y values were negative, say for example down here, it would be pointing off to the left, and so on and so forth. If you're along the axis, maybe I would just draw a dot right there because those vectors are going to have no length. Now we could focus on the curve, which is moving along the unit circle, and I should also specify a direction. I'm going to say counterclockwise. Okay, so let me actually go and plot this. This is going to look like traveling around in a circle counterclockwise, and I put that little arrow at the end just to indicate which direction is going, in this case, the counterclockwise direction. So that's sort of what it looks like. And now I want to turn to actually computing what the work done is. So what's the formula? Well, we saw this last class. The formula for the work is the line integral along a curve of the vector field f dotted with the unit tangent vector ds. However, we then said, well, that might be fine for the definition, but there's an easier way to compute this if you have a given parameterization. So the way I'm actually going to compute this is with the alternate formula, the integral from a up to b of the function, or the field rather, evaluated at the position function, so f evaluated along an r of t, where r of t is your parameterization for your curve, dotted with the derivative dr dt, and then finally integrated with respect to t. And it's this formula that I'm going to find particularly useful. Now, what do I need to do to actually be able to compute this? The field I know. If you recall, I have the field written there in the problem. But the r of t I do not. So I need to figure out how can I come up with this r of t and then subsequently dr dt. That is my big question mark I need to figure out. So, well, this curve, this r of t, is the parameterization for my unit circle. So that's my first objective, is to figure out this parameterization for this unit circle. Now, we've seen this parameterization many times before. It's just the normal unit circle. So the parameterization is r of t is equal to cosine of t in the I hat direction and sine of t in the j hat direction. I don't have to think very hard about what it's going to be because it's just one I know. I also will specify, as I always should do, that this is between the values of t being 0 and 2 pi. I have to specify those limits of integration. Indeed, they're going to become the a and the b in my formula, the 0 and the 2 pi. If I know r of t, I can also compute what r prime of t is going to be, which in this case is minus sine of t, the derivative of cos is minus sine, in the I hat, and then the derivative of sine is cosine of t in the j hat direction. So I'm now able to plug everything into my formula. What is my work? Well, it's the integral from 0 up to 2 pi, that's my limits of integration. Now, the field was just y in the I hat direction, and so the y component along the particular position vector that I have is just sine of t, and so my y gets replaced with a sine of t in the I hat. And then the field also had a 0 in the j hat. I may as well write it explicitly, but you don't have to if you don't want to. Then dotted with the r prime, or the dr dt. And so this is going to be a minus sine of t in the I hat plus a cosine of t that won't matter in the j hat, but we'll write it down nevertheless, and then integrate it out with respect to t. Okay, so this is the integral that I want to focus on, and now it's just sort of a computational problem of can I execute this? Well, let's do the dot product first. integral from 0 to 2 pi, I'm not going to change that at all. The two I hat components are going to come together. I see I have a minus sign, and so I'm going to have a minus sine squared of t. Then a 0 times a cosine gives me a 0. And then finally integrated with respect to t. This is a standard calculus 2 problem. It's just integral of sine squared. There's a little trig identity we can use, 0 up to 2 pi of minus, and then it's going to be 1/2 1 minus cosine of 2t, integrated with respect to t. The cosine 2t term, because it's being integrated over its period, is just going to be equal to 0, one of our nice little tricks. The minus 1/2 integrated between 0 and 2 pi is just going to give us the value of minus pi, and so that is the work done final answer. Well, perhaps we should scroll up to the beginning and then look at the vector field to see, well, does that make sense? Does it make sense to have a negative work in this context? Now, let's just imagine going around that circle. Remember, we went around it counterclockwise. So if you had sort of come along here and were hanging out at the top, a tangent vector at the top of it would be going off to the left, but the field is going off to the right. Likewise, if you were sort of carried on and went down to the bottom here, a tangent vector down at the bottom would be going to the right, but the field would be going to the left. So the point is, the particle is moving in the opposite direction of where the force field is pointing, and this is what gives this overall negative sign to the amount of work done in this particular example.